want to start off with a PowerPoint slide.
Okay. Okay, we are live. Yep.
So weird, my phone doesn't work.
Okay, folks, it's about that time. Thanks again for showing up to our Essentials of Physics class. Where we left off on Friday, we were considering this question. What must be the minimum length of a plane flat mirror in order for you to see a full view of yourself? So I'm hoping all of you have had a chance to think about this question between Wednesday and today. So go ahead and show me your letters. Okay, what's it look like on chat?
Even split between E and B. I think one or two more E's.
Okay, any A's at all?
No.
Any C's?
No.
Any D's?
No.
So it's only B and E are the ones that people are choosing. Interesting. Could I get a volunteer to defend why B, or 1/2 your height, is correct?
I can try to explain it.
Please do.
So I was thinking about this after we left on Wednesday and kind of playing around with other mirrors and stuff. And it says that like how far away you must be in order to see a full view of yourself. And I didn't really think it was the distance from the mirror, because if you had a really small mirror, the distance you'd have to travel away from it, like you wouldn't be able to see yourself anymore. Like with your eyes, like you wouldn't be able to like see it. And so I thought it would just depend on like the height of the mirror. And so 1/2 your height, I found to be what worked the best for me in like my own house.
Okay, so you actually did some experimentation. You tried different sized mirrors. It looks like about half your height would work.
Yeah.
Okay. Could I get a volunteer to defend why E is correct, that it should depend on your distance from the mirror? We actually had more people choose E than B, so I'd really like to hear somebody's viewpoint on this. Mr. Anderson?
For me, this is also kind of based on my experience in that the farther you stand back from a mirror, the more of yourself you can see on it. So as long as the mirror is positioned decently, if you stand a decent distance enough away from it, you should be able to see yourself entirely.
Okay.
Granted, as we mentioned before, with some of the smaller mirrors, you'd have to stand so far back that you really wouldn't be able to get a good look at yourself anyway.
Okay, so pretty much both of the defenses are relying on personal experience. Does anybody have anything to this discussion they'd like to add? Anything showing up on chat? Well, folks, I'd like to have some discussion. It certainly was not unanimous, but it's either B or E. I will just state right off the bat that it's not A, it's not C, and it's not D. It's either B or E. Half your height, or it depends on the distance. It's one of those two possibilities. So please, let's have some discussion.
I don't know, that's hard. I feel like it could be either one of them.
We had a discussion online.
Please read it out loud.
Doesn't it also depend on where your line of sight is?
Let's say that you can adjust your position in your line of sight no matter where the mirror is. So we're not talking about having the mirror flat and you're looking edge on it. We're presuming that you can position yourself in an ideal position at any given distance from any given mirror. So no, let's just say that that's not relevant because you can always move. Anything else showing up? Well, I kind of was hoping for a bit more discussion of this and maybe some reasoning based on what we've talked about as far as angles of reflection and angles of incidence. But go ahead and show me your cards and hit those letters on chat.
I kind of thought about the angles of incidence, but I don't know how I could really explain it without a good diagram.
Okay, what's it look like on chat?
Still about an even mix of E's and B's, but more B's this time.
Okay. Well, fortunately, science is not a democracy. The ultimate authority is always experiment. So I don't have a mirror that's about half the height, but I do have a certain size mirror. And we could address the validity of E if the amount of that you can see in a mirror will in fact change depending on your distance from that mirror. So I'd like a volunteer to help me out with this. Someone here present? Ma'am? So if you could just stand in the aisle. And let me see, I'm gonna go, so 2 desks away from you. Tell me where to tilt the top of this mirror so that you can see barely the top of your head. Where do I have to tilt it?
Tilt it up. Yeah.
Okay, can you barely see the top of your head?
No, tilt it down. Yeah, about it.
Okay, put your finger on your shirt to the lowest point on your shirt that you can see. So right about there.
Yeah.
So you can see pretty much your belly button and the top of your head. Okay, let's double this distance. So you go back.
4 discs and desks.
Yeah, one more desk, and I'll go forward 1 desk. So no, move forward towards me. Yeah, right to the edge of the table that's near you. No. Like along a line. So no, to the table that's here. So I want you.
Oh, this one.
Yeah, right there. So go back so that your eyes are right on that line. And then here. So we've exactly doubled that distance. Which way do I need to tilt the mirror for you to barely see the top of your head?
Yeah.
How far down on your body can you see? Looks like the same place. Let's have our distance. You stay right there. And I'm going to hold it so that you're just 1 desk away. Which way do I have to tilt the mirror? Okay, how far down on your body can you see? Same. So no difference. I'm not counting on my hands being steady enough so as even to triple that distance, but we had a separation of about 1 meter, about 2 meters, and about 4 meters. And no difference as to how much of her torso she could see. Man, what's your name?
Lauren Smith.
Okay. But let's actually see if we can justify that using the law of reflection. So if you have a mirror, let's see, you're standing in front of a mirror.
Do you want me to move that door, Steve?
That's okay. You're standing in front of a mirror. And let's just say the mirror is here. It's floor to ceiling, mirror. And in order for you to see your feet, light from your feet will go to the mirror and bounce such that these two angles are the same. Does that make sense? Angle of incidence equals angle of reflection. And so, with your eyes being close to the top of your head, not right there, but you know, pretty close, they're pretty high up there. If these are the same angles, and, well, my drawing isn't very good here. Use your imagination. Think of these as being two identical triangles. Like here, 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 and here. You see the two triangles? Use your imagination. Imagine them to be identical, because they're going to be. I just didn't draw it very well in my diagram. Same angle, same distance on this side. And so if you have one side that's the same and an angle that's the same, the two triangles are identical, which means that this distance here is the same as this distance here. And therefore, the mirror need only be this high. Does that make sense to everyone? If the angle of incidence equals the angle of reflection, just by looking at the geometry, you only need a mirror that's half your height. Something else that's kind of fun. Can I get someone else to help out? Someone with good eyes? Who has good eyesight? Yeah? Miss Baga, can she come on down and help me out here? Bana, did I say that right? I'm sorry, I'm horrible. So we have an eye chart here. And what I'd like you to do is to stand over here. And let's see. Try to read this line right here. Can you read this line right here between my two fingers?
Yeah.
What is it?
UZETS.
Wow. Okay. How about this line down below it?
ESNPTH.
Okay, maybe I should ask for somebody with worse eyes.
Except now everybody knows what the letters are.
Yeah. How about this next one down here, the second to bottom?
PHUNTDZ.
Okay, go farther back. Okay, how about the very, very bottom line?
And PXTZFH.
Okay, how's this? Keep walking backwards until you can barely make out this bottom line. In fact, like that.
I can't see it.
Okay, watch slowly until you can make out all the letters.
Yeah.
Right there? Okay. So, Colton, could you count the number of tile squares between us?
Yes.
So look at her toes and count the very next square. And try to keep the 2 meter separation. Like walk around her the other way next time. So 18 squares. Unfortunately, these tiles, yeah, let's just call it 18 squares. So now I want you to hold that and hold it right up against your chest so you can see over it. And tell me where to tilt the mirror so that you can barely see, so that you can see the bottom line.
Upward. A little bit down.
Okay, can you see the chart? Can you read the bottom line?
No.
Okay, how about now?
Nope.
Okay, how about now?
No.
Okay, how about now?
Down a little. Not really.
Okay, how about now? The very bottom line?
Yeah.
Okay, how about now?
Yeah.
Okay, I see 1, 2, 3, 4, 5, 6, 7, 8, 9 squares between us. It was 18 before. Is that what you count?
Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah.
Yeah, 9.
Exactly.
So
Half
the
of it.
image of that chart in this mirror is the same distance behind this mirror that is in front. So if it's 9 squares between us, the image looks like it's 9 squares back that way. Or 18. Okay. And something else that's pretty cool about this whole angle of incidence equaling the angle of reflection is I'm reminded of Steve McQueen and the movie The Great Escape. Anyone remember that? The movie that he only agreed to be in if it would involve him being on a motorcycle. That was his condition. And sure enough, they changed. This is basically a historical story of a escape of a group of aviators from a German prisoner of war camp. This was supposed to be history. Yet they deviated from it just for Steve McQueen because he wanted a motorcycle chase. And even though they were basing it on a book and they made assurances to the author that they would be faithful to the book, they broke their agreement. So Steve McQueen would be an actor and have that motorcycle chase. But in one scene, he is throwing basically a baseball at a corner because he's in solitary confinement and bored, and the baseball always goes right back towards him. And there's good reasons for that, in that if the corners are at right angles and you conserve momentum, a ball going into a corner, as long as it hits all 3 walls, will come straight back at you. You can do this also at just a corner where a wall meets the floor as well, but you have to be a little bit more precise in going it perpendicular to both the floor and the wall. But anyway, I have let's turn these guys off.
You want doors closed or?
No. I have a corner reflector. 3 mirrors. And if I shine a laser into these 3 mirrors, you can see the laser spot on the ceiling. It's pretty much going straight back the way, parallel to the beam that's going in. And if I were to add some smoke, let's see. You can see the beam. If I strike all 3 corners, you can see the reflected beam is exactly parallel to the beam that's coming in. Is that showing up okay in the camera? As long as I hit right in the corner, it works. I wonder if this will show up better with a green laser. Let's try that. Is that showing up any better?
I think the purple is actually better, but they're both pretty good.
Okay. Okay, so now if we look at what's going on there, if we just look in 2 dimensions, Here we have our mirror here. Light will come in at some angle. And then we'll have it reflect at, does that look close? Yeah, that'll look close. And then it'll hit this surface. We're drawing a perpendicular and, yeah, that looks like about the right angle. Okay. These two rays should be parallel because this angle, I'll call it alpha, will equal this angle. And then this angle here, I'll call it beta, will equal this angle, beta. And let's see, should I make that a bit different?
Oh,
Okay. Well, this angle right here, right there, I'm going to call that gamma. And gamma will equal 90 degrees minus alpha. Okay? And if I call this angle delta, delta will equal 90 degrees minus gamma. Because these two angles have to add up to 90 degrees because this is a right triangle, and these two angles must add up to 90 degrees as well because they form, 90 degrees between the two of them. And that means that our delta is equal to pi over 2 minus our gamma, which is pi over 2 minus alpha, or alpha. So this is alpha. And therefore, alpha plus beta must equal 90 degrees. And so if we add that up, we have 2 alpha plus 2 beta. That means we have 180 degrees in here, which means there's a 180 degree difference between this ray and this ray so that they are exactly parallel. So for this reason, we can have corner reflectors give us a bright reflection straight back. So that means that we could use something like this, similar to what we use with those glass beads in the paint that we talked about on Wednesday. In fact, this predates the use of those glass beads. And if you look in many places in Europe, where they don't tend to have snow on the roads, like Southern Europe, they will have little bumps in the middle of the road and sometimes even on the side of the road. Some people call them turtles. There's a few places you can find them in the southern United States, again, where you don't tend to have snow, that are essentially corner reflectors like this. So as you're driving down the road, you'll get these bright reflections of your headlights right there in that center line and possibly off to the side, depending on where it's at. You don't tend to have those where there's snow. Can anybody posit why? Think snowplows.
oh.
Yeah, they don't work well if you gotta have snowplows going up and down the road. But you'll see them in a lot of places, more often in Europe, and if you see them in the United States, it's only the southern US that you'll see them. But you probably have all seen these bike reflectors that you put on your spokes, your wheel, or someplace on your bike, or you stick these on mailboxes so you get a reflection. What I want you to do is look at these very, very carefully. Like, get them up real close, like face plant close. And look, you will see a repeating pattern over and over again. It is
Yeah,
basically a corner reflector.
We have an extra one here.
Yeah. So,
Needs one?
yeah, go ahead and pass these around. And I think one of the best refutations of the whole conspiracy theory that man has never set foot on the moon is one of the best arguments against it, besides the fact that you'd have to have tens of thousands of people all making the same lie, and that is simply not in human nature, is that we have placed several of these corner reflectors on the moon at each of our landing sites, with the idea that we can now precisely measure the distance between the Earth and the moon by shining a laser at where we know those launch sites would be, and we get a bright reflection right parallel to the incident beam. And what we do is we do this in pulses. In fact, this is an experiment that I was involved in when I was in college. You basically get a fairly powerful laser. It doesn't have to be a huge one, but one that you could rapidly pulse, like go pulse, pulse, pulse. And then you shine it exactly on one of these spots, align it to a telescope, and then you have a photodetector up. Has to be pretty sensitive because there's going to be a lot of intensity lost. And you wait for those pulses and you time them, and that measures the distance. Because we know the speed of light pretty accurately. And if we time how long it takes for a laser pulse to go to the moon and back, well, that tells us the distance the moon is from us. And the fact that we can do that is a quite strong indication that, yeah, we were there. We left a couple of things behind to reflect back at us. Okay, but that is a little interesting little tidbit. Okay, I've got a couple of other mirrors here. We can get reflections off of things that aren't flat. Flat mirrors are pretty common, but you'll see curved mirrors. You'll often see, I don't have any here, but what are called convex mirrors. They're curved wide. Hewitt has a pretty good picture of one of those, in that if the mirror is curved towards you, light from someplace over here could bounce and then go towards you. So it basically greatly expands your field of view. And these are great to put like near corners of aisles where people might be going by with forklifts or whatnot. And so you can basically use these mirrors to see around corners. They're pretty handy. And also, wherever you want a wider field of view. Another place you find these is on the rear view, the side view mirrors. You sometimes have a little teeny mirror at the bottom that's one of these convex mirrors. That even though you're looking at the mirror, because it's curved, you can actually have a much wider field of view than what you can get off of just a plain flat mirror. And as you probably remember from Jurassic Park, for such mirrors, objects are often closer than they appear, and you see that as a warning label on some of these mirrors. That's because if you change that lateral positioning, it also changes where that image is in that mirror. And in a flat mirror, you expect that the image to be the same distance from that mirror that the object is. Well, that's changed. It's actually closer to it if you have a convex mirror like that. And if it's curved the other way, you have the opposite effect. But you see mirrors curved like this if you want to magnify something frequently. And so I've got a couple of these. I'd like to pass them around. And because it's curved, you also get a inversion. Your image looks upside down. So if I hold it up here, you can see yourself, and you're upside down. And you're kind of smaller. You look like you might be farther away than what you'd expect in a flat mirror. But if I bring it close enough to the point where you're within the focal point, your image will then flip right side up and get quite large. And you might see more of your face than you really want to. So you can see yourself. And bring it closer. The image gets right side up and breathe it. So these are often used for putting on makeup. Because you can get a really big view of your face if you get really close. See into every pore if you want. He's not sharing, is he?
No.
You see yourself? How about that? That's pretty freaky. Okay. And I have another example of a curved mirror here. Remember I said that a lot of magic is really physics and the use of illusion? So we're going to need to get a view of this. So a good angle of view is from about this height looking down. So basically, get a view of that pig. Is that pig showing up okay?
Yep.
Can you zoom in at all?
Not without getting closer.
Okay, you have to be higher. Yeah, see the angle? So you have to be at an angle about like this to see it. Okay, is that pig showing up at all? Yeah. It's a pretty convincing reflection, and it looks real. Are you sure there's no way to zoom?
There is no way to zoom.
Okay, how about just bring it closer, but keep that angle? Just bring it closer, keeping the same angle. No, good spoil it. Not that high. So a little bit lower angle. How about there?
That's good.
Okay, so, but look, no piggy. So, you see the pig?
Mhm.
Does it look like you can touch it? Is that? So, go ahead and touch the pig. Is that pretty cool? Have all of you seen this illusion before? Have you seen this? Okay. So, go ahead, try this like that. Okay. Condensing this. So, the way this works is, you see this? Doesn't have to be.
Reflection.
It is a reflection. And what we have is we have a toy pig in the bottom there on a curved mirror, but the top is also a curved mirror. So light from the pig hits this mirror here, bounces straight down, hits the bottom mirror, and is then focused right here to form what we call a real image. If light actually intersects at a point and then diverges from it, we say the image is real, because light actually comes from that image, versus a virtual image, in that your image looks like it's over here on the other side of this mirror. Light never actually intersects where it looks like the image is. So this is called a virtual image. But it's a real image if light physically intersects there. Basically, a real image of the sun can be used to fry an ant or cook an egg. A virtual image of the sun cannot. That's kind of a nice way to think about it. So you can create a real image of the sun using a magnifying glass to actually focus the light from the sun at a point, at which point the light would then diverge from that point and look like the sun is right there where that point was. And so that's what's happening here. Light is physically coming together from that pig. So light from, say, the left ear of this pig is going in all sorts of directions. But then when that light from that left ear of the pig comes up over here, all those rays that went off in all sorts of directions from that left ear intersect right here. And so now if you're looking at this from a distance, it looks to you like that left ear of the pig is right here where those rays converged and then diverged from again. And that's true from no matter where angle you look at, that's where it looks like all the light comes from. So we call this a real image. And in the back of the room, I've got a larger concave mirror set up. And I'd like all of you to walk up there and take a look at it and see if you could shake your hand. So basically, this is one where you will get a real image of yourself and your hand, and see if you can try to touch your fingers. It looks like it's pretty freaky. So go ahead. I'd like everybody to take a chance to go up there one at a time to that mirror, and then just try to stand in front of it and reach out to try to touch your fingers. You have to be a bit closer. So reach your hand out far in front of you and look for the image of your hands and see if you can touch your fingertips. You'll note that your image is upside down, so your hand that's reaching towards you is going to be upside down. But it can actually be quite convincing. The image looks quite real. You might actually have to crouch down a little bit if you're a bit too tall, but I'd like everybody to get a chance to try that. Now, we talked about how light has several properties. It travels in straight lines, it bounces, and it bends. Actually, before we get into that, I want to say something about persistence of vision. And that I mentioned that we're rather susceptible to a large number of illusions. Well, one of these illusions is called persistence of vision. And it has to do with how our brain deals with the fact that we have to blink frequently. And there's an expression, it was over in the blink of an eye, implying that an eye blink is a very short period of time. Well, it's actually a whole lot longer than you might think. Remember, I discussed the sense of precognition that we have, where our brain creates basically visual images of what it expects to be the case by the time your brain ends up processing stuff from the past. Well, your brain also fills in the blanks when you blink. And then when you blink, it's like, oh, my vision was hardly interrupted at all. I barely perceived the fact that my eyes were closed for an instant there. That's because of when you blink, your brain fills in the gap. It basically creates an image for you to perceive that it anticipates would have been there during the time your eyes were closed when you blinked. And sometimes, if something is changing rapidly, we can be tricked by this. So if I have a laser and I shine it on the wall here, I get a laser spot on the wall. And if I move the laser, the spot on the wall moves, so I get a moving spot on the wall. But if I were to move this spot very, very quickly, it stops looking like a spot and starts looking like a line to our eyes. An oval, kind of a curve or something. Can I do a circle? I can't do a circle. I can do close though. Well, if lights are off, it might be better. Yeah, let's try it on a different wall. Actually, no, since you've got that camera rigged up, let's try it on the front wall. Okay, so there's on the blackboard, move it around, you can see a moving spot. Move it quick, it stops looking like a spot and starts looking like a line or a symbol. But really, all that's there is a moving spot. And the reason we perceive it as a line instead of just a moving spot is this persistence of vision. Your brain is telling you, oh, I must have blinked, and it's filling in a gap. And for this reason, movies and television are possible. When you watch the movies, you're not watching a series of moving pictures. The pictures aren't moving. You're seeing a series of still images. Go on YouTube, you can go through a video frame by frame. Like one of my favorites was a snowboarder, going off a jump and going all the way across the road. In one picture, he was here, the next picture there. And each successive image had him moving a noticeable distance, like almost the length of his body between each frame. And so really what your eyes were seeing was a picture of a snowboarder here, then here, then here, then here, then here, played out in rapid succession. But because you're presented with images like that, an image here, then here, your brain tells you, oh, I must have blinked, and so it fills in the gaps. So when you play a video like that, your brain will insist you see continuous motion, even though in one frame a person's arm might be here, the next frame it's here. At no point did any light reach your eye where the arm was somewhere in between those two places. Yet your brain will insist that you saw it move continuously because it thinks, oh, I must have blinked, and it naturally fills in the gaps. So without this adaptation, movies as we know them simply would not be possible. Neither would television, because the same things happen in television. You have a series of still photographs sent to the screen, and you're tricked into thinking you see motion when there is none. Okay. Let's go to the next slide on the PowerPoint. Yeah, this one. So let's say it's near the beach. Say down at Bear Lake, for example. You've got a parking lot and you've got loose sand. And you got a group of sprinters. They start off at point P, they want to get to point Q, and they want to get there as quickly as possible. Given that you can't run as fast in loose sand as you can on the parking lot, what path do you think a smart sprinter would take to get from point P to point Q the quickest? Path A, B, C, D, or E, or in fact, will all paths take the same amount of time? Think on this, please. Okay, show me your cards. What are you thinking? There is no G. So it's either A, B, C, D, E, or F. There is no G. Okay, so what's it look like?
All E's, one D on chat.
All E's, one B, huh? Okay. Could I have a volunteer to defend D, please? And let me put a caveat that the sand, yeah, it slows you down, but it's not like you're moving like the knights in the movie Excalibur, okay? Again, I'm kind of dating myself there. In that you can still run in the loose sand, just not as fast on the parking lot.
Yeah, I was gonna say it kind of depends on how much the sand slows you down.
Could I get a volunteer to defend D, please? Hey, Mr. Harry, I see that you chose D. Could you chime in, please, if you don't mind me picking on you?
Yes, sir. Can you hear me?
Yeah.
That one just looked the most logical to me. Running on the parking lot, you're able to do that at a faster rate than on loose sand. So just for a pretty good distance, you can run on the parking lot, and then you won't be running on the sand for as long.
Okay. Could I get a volunteer to defend why E should be a better way to go?
I could do that. I would say E just because it's the shortest amount of time on the sand, so you'd be able to get there faster.
Okay, so E is clearly minimizing, no other path has less time in the sand than E. Okay. You know, I don't think we'll need discussion here because really it all comes down to E or F, depending on how slow, sorry, not E or F, but D or E, depending on how slow you move in the sand. And E has a lot of distance, but it does minimize the time in the sand, which you have to go a lot farther along through the parking lot to get there. So as long as it's not an extreme amount of slow down in the sand, something close to D is probably a bit more accurate. It might start to be close to E, but in no cases are you going to go exactly perpendicular to the parking lot if you want to minimize the time. Because the closer and closer you get to a path like E, the more and more distance you end up having to travel. So there's going to be a bit of a trade-off. But this is kind of how light works. And to remember that light, when it goes through a material that it's transparent to, the light is absorbed by molecules and re-emitted, absorbed and re-emitted, absorbed and re-emitted. And it slows down. We could talk about the speed of a large number of light particles going through material being slower as opposed to what it would in a vacuum. And there's a principle called the principle of least time that's actually a pretty good explanation for the amount that light bends when it goes through a material, in that light will minimize the time it takes to traverse a material. And so if it has to slow down, it's going to start taking paths like this. So if we shine light at, say, the surface of a water, you'd expect to see it bend kind of like this. And let's see. I have a little trough of water here, and let's see, we might need the doors closed for this.
You got that? Yep.
Okay, so I've got a tank of water here, and you should be able to see light that's reflected off of the top surface of the water, and then it goes into the water and it's bent. It reflects off of the bottom surface, and that then goes back out. So we see some kind of nice rays here. But you see that the light is bent when it goes into the water. If I shoot it straight down, there's no discernible bending, but as soon as it hits at an angle, you can see that we get quite a bit of bending. And I can do it off over here, and it's actually kind of pretty. You can see a reflection off on one side, light bending as it goes into the water, hits the top surface of the water, it bounces around. And look at what happened here. If I have an angle large enough, we have light escaping the water and hitting the wall. But if I decrease that angle, boom. At this point, we have what's called total internal reflection. All the light is now trapped inside the water that actually makes it into the water. Now some escapes. Now it's all trapped. Now it escapes. Now it's trapped. See, this is a very critical angle here. And at angles larger than this, the light is always confined to within the tank until it hits the far side. So we can get this, it's like tracing the lines backwards. If I go at a very, very steep angle, almost horizontal, you can see there's a certain angle at which the light goes into the water that I can't really make it bigger. And conversely, it's on the other side. There's an angle at which, if the light hits the surface of the water from underneath, it's going to be totally reflected internally. Here we get some light escaping, there we don't. Okay. And we could use this to actually channel light into materials. So I have a bent piece of plastic here, and if I shine laser light into it,
Whoa.
It's confined to that plastic until it leaves the other end, even though there's quite a bit of bending going on. And frankly, I'm not able to shine it in at an angle large enough to have it escape. And I can do something similar here with this curved piece. And the lights, except where it's scattered off of imperfections, it goes all the way through these loops until it comes out the end over here. So we can basically channel light through materials. And this is pretty useful.
This tube isn't hollow or anything, is it?
Nope, not hollow, it's solid plastic. And this is the principle behind fiber optics, in that I've got a number of little lamps here. Let's go ahead and hand these out. You can pass that out. There's a light source in the bottom, and light goes up through these little fibers. And it stays inside the fiber until it reaches the end. And actually, we're out of time. This is where I want to start up that on Monday, is talking about fiber optics and their importance. There it goes. But we can use light for communication in this way. And it provides a lot of advantages over what we used to use for communication. And I'll talk more about this on Monday. Thank you for your attention. Have a great weekend, folks.
Great weekend, Dr. Steve.